Greetings, my Calculus BC or Calculus 2 friends out there. Mr. Record here from Avon High School, and we are going to embark on a new topic that I call topic 8.14. Now, I'm going to probably say this more than once. If you follow the course and exam description from the College Board, whether you're a teacher or a student in high school, you know that there is no such thing as topic 8.14. Unit 8 ends at 8.13, right? Arc lengths of rectangular functions. But what we're going to do here is I'm going to tack on a few extra topics that will round out what would be a really robust Calculus 2 course. But I want you to know that all of the content that will be covered, not just in this video, but my other videos that pertain to this fictitious topic 814 will not be tested on the AP Calc BC exam. But I'm sure if you're a Calc 2 student probably tuning in, you might be enjoying these videos as they might give you a little bit of help in your college course. So topic 14, work, 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 work. Yep, maybe Rihanna sung it best, but that's going to be the name of the game over these next few videos. And so what I wanted to do here is just kind of recap a few kind of things about why we study this, and just to kind of highlight the key points here. The concept of work is very important to scientists because we always, as scientists, need to be abreast of how much energy is needed to perform various jobs. That might be from bringing in a large crane to lift a steel girder, compressing or stretching a spring in a hydraulic lift. Um, Actually, the hydraulic lift itself is probably going to actually perform a little bit of work as well. A rocket being propelled up to the sky, a truck pulling a load on a highway. So really, there are seemingly quite a few applications of this. And the thing that we always must kind of remember is there is a basic non-calculus definition of work. And that is work is equal to the force applied to an object to move it, multiplied by the distance that the object is going to move. That's in essence what the work definition is. But that is a very contrived version of the definition, and one that doesn't require calculus. So for a very easy version of that, we can look at our first example right here, and it mentions that we want to figure out how much work is done in lifting a 50-pound object a entire distance of 4 feet. So if we follow our typical work equal force times distance, what we find out is that the force that is required to lift a 50-pound object is indeed going to be the same as the weight of that object. So the force is 50 pounds. And I'm going to go ahead and put the units in here. Now, we probably need to pause right now and make sure that we understand that I am using this sort of United Kingdom imperial unit approach with pounds and feet, not to get confused with the metric version of what many of you are probably used to in some of your exposures with work. Newton meters is a thing, and it will happen eventually within the content of my curriculum. I don't want you guys to get all confused and say, oh my gosh, this stuff isn't going to be helpful because he's talking about feet and pounds. And I understand there's not very many countries that still use feet and pounds. America is one of them, right? I think Liberia is another one, and maybe Myanmar is another one. Not very many countries that still do this. Maybe one day we'll switch completely to metric as Americans. But for right now, I want us to go ahead and go with the flow, and we're going to use our pounds for our force. Basically, what that means is if this box here in this picture weighs 50 pounds, if we apply any other kind of force to it less than 50, it's not going to move off the ground, right? That 50 pounds is kind of built into the Earth's gravitational pull upon that object, okay? Right? Now, don't want to ever think that the 50 pounds is the mass. That is an entirely different idea, and that's not where we're going here. So the distance that says that we want to lift that straight up in the air is 4 feet. And so if we multiply 50 times 4, we of course get 200. Now the weird part, the units. Typically in this imperial system, we're going to say foot pounds, and we'll put a dash in between them. Foot dash pounds. And so I won't get into a lot of detail about how you would interpret that. It's not important that we convert it to Newton meters. That's not what the point of this problem is. The point of this problem is to recognize that when we lift this 50-pound box, whether it's right down here at its beginning of its journey, or if it's somewhere in between reaching its 4-foot height, the amount of force that's going to be applied to it is going to be a constant 50 pounds to keep it in that state of motion. Now, a lot of problems aren't going to act that way, and that's where calculus comes in. So if we have a variable force, then things certainly are going to change. What that's going to mean is that we're going to have these incremental amount of works that are done throughout the process of moving the object. And those incremental amount of works are likely going to carry different forces on it. For example, let's say that we're lifting this 50-pound box, but that 50-pound box is full of sand. But that box has a hole in the bottom. And throughout this process, sand is pouring out of the box. And so as the box rises and rises and rises, it's becoming essentially lighter, thus requiring a different amount of force to lift it. Higher it goes, the lighter amount of force, the less amount of force is required. And so whenever we have that variable amount of force, we need calculus, because all of those incremental work answers are going to be different throughout the process. And we're going to, of course, add them all up. And of course, we want the amount of sections of that work to be infinitesimally small, right? And so when that starts to happen, we get an infinite number of sub-intervals of work. And so it's that whole idea of the limit as n approaches infinity, of the summation starting to beget a definite integral. And we talked about that a lot in my video series back in Unit 6. And so now we have force times distance. That dx is going to act as our distance, and the force f of x is going to still be there. And then when we integrate across the boundaries, that's going to do a more specific job of defining that total distance. And hopefully that helps out, because that's going to set the stage for the other, 6 problems that I'm going to talk about in my video series on work. Down below here on the front page of my notes, I give you a couple of general types of variable force problems that seem to be sort of grouped into 2 different categories. And I don't want to necessarily make this really super confusing, but the example that I just kind of illustrated with the box with the sand pouring out will very likely fit into category 2. That's when you move an object and it becomes increasingly easier or increasingly more difficult as that object or that slice of work moves throughout your interval. For example, when you're raising a chain, right? Say you've got this chain with these links and it's fully extended. And let's say that you got a person that's on the top of the box right here, right? That's where he would be, right? Reaching out his arm, and he's going to lift that chain up. Well, as this person lifts that chain up, the links of the chain are going to rest next to him or her as the chain gets shorter. Well, you can certainly see that a time will come when there's not as much chain to pull up, thus making that chain lighter. And so that would be a really good example of where the dx part is sort of encompassed in the force that's becoming incrementally different. Okay, or over here, the dx part is going to more likely pertain to the small distances of work that we're going to do throughout the problem. And so you've got, like I said, a couple of different philosophies, but when it comes down to setting up the problem, they're really going to be done somewhat similarly. And so it's really important that you guys tune in to some of these future examples so that you can really get an idea about how to solve work problems with variable forces. All right, hope this helps a little bit. Keep watching.